Welcome, everyone. Excited to see you all here today. My name is Prachi Vakaria. I'm the founder of Wiser and really excited to see you all today. Today, we have a really special program for you. I'm really excited to share it with you. After the program with Dr. Scott Crowder, we will get into orientation really quickly. But really great to see you. Welcome to the Wiser 5th edition for the summer program. And let's get started. Over to you, Abhinaya.
Yeah, thanks, Prachi. Hello, everyone. Good morning, and welcome to the WISER Summer Program 2026. If this is your first time participating in a WISER program, welcome. We are excited to have you here, and if it's not, welcome back. We are equally excited to have you here as well. So quick introductions. I'm Abhinaya Gnanasekharan. I'm the technical program lead here at WISER. I'm also a senior scientist in fault-tolerant quantum algorithms at IonQ. And yeah, let's get started. As you all know, this summer we will be going deep into one of the most important topics in all of computing, optimization. In particular, how the field is being shaped by classical computing, rapidly advancing AI, and the emerging powers of quantum computers. Before we dive in, just a couple of bookkeeping things to get out of the way. If you have any questions for the speaker or for the team, please post it on Discord in the live session. And you should have received the Discord link with your registration email. Yep, I think that's it. Let's dive into the program. We have our keynote speaker here with us today, Dr. Scott Crowder. Scott is the Vice President of IBM Quantum Adoption and Business Development. He leads the commercialization effort for quantum computing and IBM Quantum's efforts to create a globally diverse and skilled workforce required to unlock the potential of quantum computing. Scott brings remarkable breadth to this conversation, from his early work as a lead engineer on the industry's first logic-based embedded DRAM technology, to serving as the CTO of IBM Systems, to shaping IBM's vision for the next generation computing infrastructure. He holds a PhD in electrical engineering and an MA in economics from Stanford, and degrees in electrical engineering and international relations from Brown University. We are honored to have him open our program this year. Please join me in welcoming Dr. Scott Crowder. Over to you, Scott.
Thank you. Welcome, everybody. So my name is Scott Crowder. I've got the privilege of help running the quantum program here at IBM. I am a long-term IBMer. As mentioned, previous to this role, I was CTO in IBM Systems, which is how I got involved in quantum computing. And honestly, I didn't get excited. I didn't get interested in it for the sci-fi come to life part, which is definitely true in quantum computing, teleportation, spooky action at a distance, flux capacitors, all those kinds of wonderful things. I actually got very excited about it because it was basically a brand new computational tool, and it was very, very early in the adoption. And I'm personally very enthusiastic about trying to make quantum computing, learning quantum computing, building the skills for it as widely available as possible. And that's actually why I got very passionate about quantum computing back 10 years ago now in the program. So today I am going to, and I apologize in advance, give a fire hose kind of keynote here. I'm going to start out talking about what is quantum computing, where we are today with quantum computing, what's the path forward. I think this is an important foundation for talking about any of the applications of quantum computing, understanding where we are and where we're going with the technology. And then I'll talk about quantum algorithms for optimization and give you, some examples from industry. And then some of the recent work that's being done at IBM on AI for optimization, leveraging graph neural network approaches to try to solve thorny nonlinear optimization problems using AI approaches as opposed to quantum or classical approaches. Okay, so let me start out, and then hopefully there'll be some time for some questions and answers at the end. So let me start out with just the very, very basics, very high level, and I'm not going to get into the details of superposition and entanglement, et cetera, et cetera. I can answer questions on that, but really going to focus more on the technology, what is it good for, where is the technology, what we think is going to happen in the next couple of years, and some of the algorithmic approaches leveraging this new computational tool. At its heart, we see quantum computing as a new computational tool that adds to the computational tools we can use to solve problems that we want to solve. The major difference is that the computational tools that we know and love, the classical ones, leverages binary arithmetic to do actually quite an astonishing amount of things just by adding zeros and ones. We all kind of know how great CPUs are doing for are doing for business process tasks and standard arithmetic, multiplication. We know that leveraging GPUs, we can do tensor math very effectively, matrix multiplication. But those techniques, those computational tools are based on binary arithmetic, and there's limitations to what you can compute with them. And the easiest way to kind of explain that at a high level is if regular old classical computers were good at computing everything, there'd be no cryptology, there'd be no cybersecurity. Our cybersecurity is based on the fact that we've got math that in one direction is easy and in the other direction is hard. Quantum computing leverages a couple extra instructions that we add based on superposition and entanglement to allow us to do different types of computation than what we can do using binary arithmetic on classical algorithms. And again, the most famous example of that is back in 1994, Peter Shor came up with something called Shor's algorithm, where he came up with this concept of how he could do factoring using quantum information science exponentially more efficiently than using binary arithmetic, adding zeros and ones. And the reason that ties into cybersecurity is because the math behind factoring is how we do a lot of our asymmetric cryptography today. It's just one example of a kind of math problem or computational problem that this new concept of using quantum mechanics to do in information science allows us to do that we can't do using binary arithmetic. But the good news is that that's not the only algorithmic area or use case that people have come up with on a blackboard using complexity theory that we believe that quantum information science will be much better at. There are other computational areas as well. Hamiltonian simulation is one of them. This is simulating chemistry, nature, etc., high energy physics, chemistry of life. The second one is optimization, which we'll do a deeper dive on in a couple minutes. And this is basically higher order binary optimization. Fits well into solving Hamiltonians, which fits well on the quantum information science or quantum computational. Machine learning, we'll get to in a minute, which is the most controversial, and differential equations, solving partial differential equations. People have come up with algorithmic approaches, especially if there's nonlinearity in the differential equation, that there's a provable exponential speedup. Let's circle back to machine learning. Machine learning actually falls into a similar category as Shor's algorithm in that using group structure, group theory, I can prove that if there's certain kinds of structure in my underlying data, a quantum algorithm will find the patterns in that data that look random to any of the known classical methods that we've got using binary arithmetic. And this fundamentally is like underneath kind of like Shor's algorithm as well. But what Peter Shor proved is that factoring actually, there's structure in that problem. And then using a quantum Fourier transform, you can actually find that structure very efficiently, the remainder of a long division, et cetera, et cetera, et cetera. You can find that remainder, much more efficiently using a quantum algorithm. Similar kind of concept, you can use that as an argument for how you can find provable advantages, in binary classification kind of problems, where you can find if there is structure in the underlying data, you can find that pattern using a quantum algorithm. The reason it's controversial is because a couple of reasons. The first reason is controversial is because if I give you any old classical data set, there's no way of a priori knowing whether there's any quantum structure in that data that you can extract. It's 100% empirical. And just because it works for one data set, you can't prove on a blackboard that it'll work for any other random classical data set. So this drives the complexity theorists absolutely crazy because there's a lot of claims out there of advantages being shown for quantum machine learning that you can't rigorously prove why. The second reason why there's like some controversy around quantum machine learning is that there was a lot of work done about 5-7 years ago now around using it for support vector machines. You could find signals that show that the quantum approach is better for very, very small problems. But as people started to get to like realistically scaled problems, they ran into barren plateau, other kinds of problems that people are very, very familiar with in machine learning and AI space, and that didn't really scale particularly well. So because of those combination of problems, the machine learning space is an area that is very, very controversial, although in the long run, because there are exponentially proven speedups, it's very likely that there will be an advantage there as well. The other interesting thing around machine learning is people have realized also that quantum computers are not like GPUs in a lot of ways. So in one really important way, it is. So quantum computers and GPU-based computers are similar in the sense that you use them to run particular subroutines that is really good at computing. And then for the rest of the stuff, you use CPUs and other classical methods. So quantum computers, you can think of them as accelerators. They're not going to replace all classical computers for today. You're going to run particular subroutines on a quantum computer, just like you run particular subroutines on a GPU. So that way they're very, very similar. The difference is, and this is an important distinction with all the hype that's in the industry, is that, as I mentioned before, quantum computers run quantum algorithms which do not run on classical binary arithmetic-based systems. So when you're running your quantum algorithm, it's not like a GPU that you're running the same algorithm you would run on a CPU, just splitting it up and running it in parallel so it runs faster. You're running a fundamentally different algorithm, a different algorithmic approach. The reason why this is important to belabor is it makes the comparison of is quantum or classical better much more complex, much more nuanced, because you're not comparing apples and apples. You're comparing one type of algorithm with another type of algorithm. You're not just taking the same algorithm and parallelizing it. The other reason why this is important is because when you're thinking about the quantum algorithm, it needs to have basically an intrinsically better approach to solving the problem, because it's not just a faster flywheel. The concept that quantum works because it simulates everything in parallel, that's not true. It's not more powerful than a classical computer in the sense of it can basically have a faster operation speed. That's not true. It's not that you're doing it in parallel, kind of true, but not quite true with GPUs, that you're just taking the same thing and running in parallel. In a quantum computer, your flywheel is going to run slower, but the fundamental algorithm you're running overcomes that because it shows an exponentially more efficient way of solving the problem so that the quantum computer can do things that classical computation can't do. Where are we on quantum computing? And the reason why I belabored that point is because it's important to understand these are apples versus oranges to understand where we are in quantum computing. 10 years ago, IBM put a 5-qubit quantum computer on the cloud and said, go at it. Like anybody on the planet, for the most part, can go program that 5-qubit quantum computer. It's kind of like the sci-fi come to life moment. I can run Bell's inequality on a computer and actually prove something that took huge amounts of efforts to experimentally prove like that. I could program a quantum computer and actually run it. It's like a real thing. It's a real computer now. So flux capacitors, teleportation, all those kind of cool things came to life, and people could play with it. And they got, I got excited about it personally. But at the time, you could only run about 25 operations on it before the noise got to you and the quality of the result wasn't great anymore. We've come a huge way since then. So now state-of-the-art quantum computers that exist today from places like IBM, and I would argue from Google, Chinese Academy of Science, and probably Quantinuum, you've got quantum computers today that can run programs that have thousands of operations in them and on order of 100 plus qubits. So you can now run a quantum algorithm or a quantum program that is way too complex to just run the exact same thing on a classical simulator on a classical computer. Binary arithmetic, you can't run the program anymore. So a lot of people use different words to express that, but that orange quantum algorithm you're running on a quantum computer of today, you can't take that orange and run it on the world's largest classical supercomputer. It just won't run. There's not enough memory space, et cetera, et cetera, et cetera. It's too complex to run there. That doesn't mean that the orange is yet better than the apple. That means that you cannot run that quantum algorithm on a classical computer. That does not mean yet that the quantum algorithm gives you a better outcome than any other known classical approach that you can come up with. And that's the next step for quantum computing. The next step is what people call quantum advantage, which is using a quantum computer gives me an answer that is better in some way than any classical approach we can ever come up with. And the reason I was harping on the apple and orange thing is to give you kind of a high level kind of intuitive feel that this is a hard problem to solve because you're proving a negative. So people are in the state now where people are coming up with plausible claims of advantage that my quantum algorithm gave me a better result. But there's a huge debate going back and forth for any of those claims as people try to come up with better classical approaches to basically now surpass the quantum benchmark. So that's where we are in the state of the art, the technology today. The other really interesting thing that's happened, and I'll give a couple examples, in the last 6 months or so, has been that those quantum algorithms, people are no longer solving toy problems. They're solving problems that they are currently using classical approaches to solve in production, or problems that they wish they could solve in production with classical. So I'll give you an example in a moment, but this means basically that instead of like simplifying my problem down to something that I don't care about, my real day-to-day, people are using quantum computers to solve real problems, which allows them to test A versus B, to test, does the quantum thing give me a better answer, or is it easier to program, or is it faster, or is my classical approximation better? Right. That's where we are today. We know that in order for us to solve those real problems, for a much broader set and much more cleanly have an advantage over classical, we need to be able to run much more complex programs. In order to run much more complex programs, to go from an order of 10,000-ish operations to hundreds of millions or billions of operations, you need large-scale fault-tolerant systems, which at a high level just means you need the ability to detect errors and correct errors as you're running your program. Our roadmap is 2029 for when that will be available to the public. Other people have roadmaps also. Get into that in a little bit. And then I brought up Shor's algorithm, and just this is not really the point of this discussion, but just to fill out the story. If you just take our IBM's roadmap and draw a straight line of what technology we're going to deliver when to the public, when you get to 2035, the line intercepts when, based on today's best known understanding of Shor's algorithm, you get to the point where you can use Shor's algorithm on a commercially available quantum computer to break today's asymmetric cryptography, which is this whole drive towards post-quantum cryptography, and we just need to change our asymmetric cryptographic standards well before we get to 2035, and you can do that on a commercially available system. Okay, so I went through all this to kind of give you a feel for where we are in quantum computing. These things are real. IBM alone has deployed over 90 systems since 2016 for external people to use. We've got 15 systems available at any given time in our cloud data centers, or that are dedicated on premises around them. There's a software stack for people to program. The one that we have contributed to, is Qiskit, because it's open, allows you to run on multiple backends. We think that's incredibly important for the adoption of the overall technology, plus the ability to integrate into HPC environments, et cetera, et cetera. And it's driving a lot of innovation. Like for technology that there was no such thing as a quantum developer or a quantum programmer, or if you wanted to publish a paper on quantum computing, you needed to build your own quantum computer in your lab. In the last 10 years, we're now actually it's over 6,000 now, papers on archive using quantum hardware or software from IBM, and you can see from other players as well. And huge interest, like this session today, in education and skill building, which is really, really important to drive the innovation in this technology. I mentioned before that a lot of progress has been made in the last 6 months on being able to run larger scale problems on today's quantum computers. And this is just one example of that in chemistry. I know chemistry is not optimization. Well, there is some optimization there, but that's not the focus for this course. But I wanted to give you this a feel because I think intrinsically as humans, we get the life sciences thing pretty well. So about a year ago, state of the art was running simulations of like ground state energies and things like that, on like 14, 20 atom size molecules. That's the size you could fit the entire number of spin orbitals into one quantum computer and run the full problem there. What has happened over the last several months is a huge amount of innovation on the algorithmic application side. So not just improving the quality of the underlying quantum computers, but also innovation on the application side. And similar things are going on in optimization, which is why I'm belaboring this point. So what some of our partners at Cleveland Clinic came up with is an approach to basically break up the problem and basically fragment the total system that I wanted into pieces. And you do that basically leveraging accelerated compute on GPUs, and then running the Hamiltonian simulation on the fragments on a QPU, and then using a CPU to post-process that data to put it back together. And they made amazing strides in the last several months using this technique, from publishing a paper back in December on tryptophan with 303 atoms to just a month and a half ago, basically extending that to putting that protein, in a solvent, which is what the real world simulation that they care about is. For like that protein is important in the oxidation of that protein, limits vaccine shelf life, for example. So doing a better digital twin of simulating that molecule in its environment could be extremely beneficial to life sciences companies, as an example. So now they've basically simulated over 12,000 atom molecules, leveraging quantum computers that we already have today. So this is, again, an example of using even today's quantum computers to solve problems at sufficient scale that is interesting. And it's very, very, very close to the best known classical methods, not quite yet claiming that it is better than the best known classical methods, but it's getting very, very, very close. And this is why people are so excited about the technology. We're working with people across a lot of different industries. Just some additional examples, exploring corrosion and material degradation for aerospace, doing optimization simulations with Moderna, et cetera, et cetera, et cetera. So how do we get from where we are today to where we can get quantum computers that will be useful broadly? It takes two things. This intro, I'm talking a lot about building better hardware and software, improving quantum computers, but at the same time, equally important is algorithmic improvements, like the one I just mentioned from Cleveland Clinic, that allow us to basically build better and better hardware, but at the same time come from the other direction and have more efficient algorithmic implementations and understand how to leverage those algorithms for real applications. And this is what this session this summer is about for optimization using quantum, but also AI methods. Many vendors have now published roadmaps to fault-tolerant systems, and I think we were the first who said 2029, but a lot of people are now saying 2028, 2029, 2030 timeframe. There's a lot of money going behind this, and I think at this point, we're fairly confident this is not a question of if, this is a question of when the world's first scientifically relevant large-scale fault-tolerant system will be developed and made available to people. Why do we have so much confidence in that? We have confidence in that because from our perspective, we've got a clear roadmap of what the technologies that we can deliver are every year between now and the end of the decade. The number on this chart you should pay attention to, very busy chart, but if you see the bird names on the bottom, those are the qubit chips. You see Nighthawk going up to about 15,000 operations, and then a big jump at Starling to go to 100 million operations. And that's that big jump of going from basically introducing the ability to detect errors and correct them as you're running your program, large-scale fault tolerance. Why do I keep harping on the fundamental of correct and to detect and correct and larger scale? Because there's a lot of FUD in the market right now on logical qubits and what's a logical qubit and error-corrected qubits and what's an error-corrected qubit. There's a very, very wide range of that. But as a user of a quantum computer as a computational tool, what you really care about is what is my register size? How many qubits do I have to program with? And how many operations can I run and get a good quality result? And then the third one is how quickly, what is the throughput of my computer? Those are the three things that you should care about when you're looking at a roadmap from us or from anybody else. Number of programmable qubits, how many operations can I run, and how quickly I can run them. Everything else at this point, frankly, is just noise. Why do we have confidence in our roadmap? One of the fundamental reasons why we have confidence is because we think we've demonstrated most of the underlying science in theory. Now it's just, in air quotes, a lot of engineering work. One of the breakthroughs that happened in the last 5-6 years is much more efficient error-correcting codes, which allow us to build large-scale fault-tolerant computers that aren't the size of a warehouse. If you heard or remembered 5-6 years ago, people were talking about building warehouses for a quantum computer. With the improvements that we've seen in the error correction code approaches, that is no longer the case. And that's why we're very confident, and that's why we published a roadmap for 2029. The downside is much more complex engineering. We need to make our qubit map into this torus shape, and it needs to connect that way. So it's much more complicated engineering. But we've got a roadmap for that too. And we're going to demonstrate the pieces of each part of that by 2028, and then release it to the public in 2029. This is what a quantum computer of today looks like. That centerpiece where the octagon is that fancy chandelier looking thing that you all see the pictures of, sits in there, isolates the qubits from the rest of the universe. The wings are your control electronics. Quantum computers work by singing to your qubits at a certain frequency, a certain energy for a certain time in order to get them to change their state. And the black boxes in the back are where the cryogenic equipment is, and your regular old servers that hold the classical state do the post-processing and pre-processing. That's what state-of-the-art looks like today, up to 1,000-ish kind of qubit devices. And then over here on the right, is kind of a rendering of what a 2029 fault-tolerant quantum computer is going to look like. Major difference is your cryogenic environment is all connected together. So you can have one cryogenic environment to build a modular system and build a large-scale system. And then the larger system to the right is the 2033 or mid-2030 system, which would be cryptographically relevant. Just a picture of what it looks like, give you a scale and size. All right, so apologize for spending a half hour doing like a fire hose on quantum computing. Where are we? What's the next steps, et cetera, et cetera. Now I'm going to pivot, talk a little bit about specifically optimization. So classical optimization solvers may be approximate methods in a lot of cases, and they're all very usually heuristic as well, but they're really good. There's existing well-tested methods like CPLEX, IP-opt, et cetera, Roby, blah, 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 that can do a pretty great job at approximating a lot of different types of problems. But there are many problems still that remain hard, even at relatively small scale. And a lot of optimization outcomes are worth a lot of money or a lot of value if we could do a better job of solving them. So there's a lot of interest in leveraging these new technologies, both AI and quantum computing, to see if we can do a better job of optimization over these best known classical approximate methods. Basically, supervised and unsupervised learning to optimize approach. So they're trying to solve large nonlinear continuous programs faster than you can do it using the classical approximate methods. Quantum is a little bit different. Quantum is also focusing on solving single and multi-objective combinatorial optimization. It has algorithms that you can write on a blackboard and do your complexity theory based on the underlying math. For certain types of problems, you can prove that there would be a speed up for the best known quantum algorithm over the best known classical algorithm when quantum computers get larger, more powerful, et cetera, et cetera. That also motivates heuristic development, and I'll talk a little bit about that in a second. So a lot of the focus on the quantum side is understanding the heuristic approaches and doing benchmarking, because it is heuristic, against the classical and the AI-based combinatorial optimization solver. All right, so for quantum optimization, like anything else in quantum, there's lots of hype, lots of FUD. You hear all the time, quantum computers can evaluate all the possible solutions at the same time. Now, that unfortunately is not true. That's not quite how it works. On the flip side, you'll hear a lot of people say quantum computers can achieve at most a quadratic speedup, leveraging Grover's algorithm type approaches. That is true to a point. That is true that the quadratic speedup for those problems that you're leveraging a Grover type approach in that. But the situation is a little bit more nuanced than that. There are different types of algorithms and algorithmic approaches. It's not just for quantum, but for classical as well. But the quantum, there's those that can provably give you exact algorithms, guaranteed to return you a global optimum solution. And that's where, for most, like the NP hard problems, at best you've got a quadratic speedup. And this is where that Grover's search algorithm comes from, and a lot of the early research into quantum optimization really was heavily focused there. But there are other types of problems, factoring isomorphism, blah, 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 convex optimization, where people have proven, like on a blackboard, that there can be exponential speedups with Shor's types of algorithms and different kinds of algorithmic approaches. In addition, you've got those that have provably approximate solutions with, with bounds on how far off you can be. And for those, also, there's been a recent publications that show exponential speed up for some of those. And then finally, because we know that there's these kinds of potential speed ups, we also are very interested in looking at heuristic algorithms. And we know that in the classical world, heuristic algorithms are some of the ones that are used the most and give you the best answers. So we need to do similar things on quantum approaches. So we believe that disruptive quantum advantage and optimization is possible, but especially in the near term, it's going to be heuristic. So we need to test them and we need to benchmark. Combinatorial optimization is where most of the effort is these days, because even small instances can be very challenging classically, and because it's less of a bottleneck from an IO perspective. And specifically for quadratic and higher order binary optimization, it's actually a very good map to basically ground state type problems for Ising Hamiltonian. So there's a good map of those type of problem structures, especially on graphs, to basically what quantum computing is actually doing on the system from a calculation point of view. One of the best known methods is quantum approximate optimization algorithm, which was inspired from an adiabatic algorithm. And you basically do multiple rounds to optimize, parameters within the algorithmic approach. And you can have performance guarantees in certain cases, as the number of rounds goes to infinity. But there are a lot of challenges with using QAOA. The first is that today's quantum systems are limited to about 100 qubits, which usually, if you're going to do direct encoding, means that many binary variables. And frankly, most classical approximate methods work very, very well on that level of variables if you're only dealing with like one constraint or one objective function, especially if it's linear. Now, those devices will scale more in the future, but right now it's a limitation. Noise is absolutely a challenge, especially with dense qubos, because if your matrix is very dense, your circuit depth gets really long. When we get to large scale fault tolerant systems, that will be much more approachable. But for today's systems, the sparser the matrix, the more approachable it is today. In order to do it, you need a lot of samples to get results. If you're doing a purely variational approach, that turns out to be fairly slow. The fastest quantum computers today that are based on superconducting qubits, or their sampling rate is on the order of kilohertz to 10 kilohertz, which is, order of 100 times slower than, CPUs. So there is a speed issue there. If you're going to like an ion-based system, you can multiply that by a factor of 1,000 slower. And then QAO is in general heuristic, so it's very, very problem dependent, and it's not known upfront. So like heuristics in classical, it's going to come down to lots of benchmarking, but also seeing where it works and then seeing the adjacent kind of problems that gives you confidence that it may work there as well. So benchmarking is critically important. All that being said, there's an increasing number of demonstrations using quantum algorithms that are too large to run on the world's largest supercomputer, taking these quantum approaches, and people are starting to make claims of a quantum advantage for some of these QAOA-ish based approaches. Again, completely heuristic, needs to get validated against best known classical methods. But we are now at the point, like I said before, where people are running real world-ish scale problems on today's quantum computers and comparing it to classical approaches. That includes some of our partners who have basically created functions, so basically black box quantum optimization solvers that people can actually go and try. So a lot of the focus now is on understanding basically what types of problems we will have the quantum approach be better than the best known classical approach first. There's like an optimization working group that exists across lots of different institutions working together. And what they're trying to do is create this benchmarking library, which they came up with like the intractable decathlon of like problems that are really hard with best known classical approximate methods that they believe quantum has a strong potential advantage for. Putting out a bunch of these to give you examples across multiple application domain kind of areas that they're benchmarking, and working with researchers in a lot of different institutions. Here's an example of a graph problem, a weighted graph problem that Eon and STFC worked on, where they're basically leveraging a QAOA based model in order to basically they're trying to do an optimization on peer-to-peer energy exchanges. These, like I said before, these graph type problems actually map fairly well to QUBO and HUBO type approaches, which make them a very interesting area for optimization work these days. Another example is a quantum enhanced Markov chain Monte Carlo for computational optimization. Again, this is with STFC. And one area that's getting a lot of traction more recently is looking at multi-objective optimization. So basically leveraging the fact that quantum computers may be good at giving you a large number of very good samples very quickly that you can then feed into classical optimization to basically create a Pareto front much more quickly than you can with just a purely classical approach. This is an area that is getting a lot of research interest right now, and very, very promising candidate because the multi-objective and or multi-constraint kind of problems are one of the things that classical has a challenge of doing a good job approximating. And the fact that you can sample much more rapidly on a quantum computer is very interesting. And this applies to a lot of different industry use cases. obvious ones in finance on portfolio optimization, insurance and underwriting optimization. But optimization comes up in chemistry of life kind of things like optimizing mRNA sequences, and then obviously a lot of logistical stuff, the grid optimization, trading optimization in energy that we were talking about. One example of that is Vanguard looking at portfolio optimization. Another example is Moderna looking at secondary structures for mRNA. Takeaways for this part, and again, I apologize to the fire hose, but I want to leave a little bit of time for questions. I want to get to AI. Today's quantum computers are already tools for algorithmic discovery. We have gotten to the point now where you can run something meaningful on a quantum computer. We need to benchmark more to understand where that meaningful quantum algorithm run actually shows any advantage or potentially will show an advantage over classical methods. And we need to think about the problems differently. And this is really where a lot of the innovation is coming from, like the multi-trajectory optimization or the Pareto front. Those are more recent. When we started this journey like 10 years ago, people were really had their heads focused on pure, here's the Blackboard quantum algorithm. What does it take to run the Blackboard quantum algorithm? Like the chemistry example I gave you now, people are now thinking about how do I break up the problem to leverage using quantum for particular subroutines that classically can't do very effectively or doesn't approximate particularly well. And how does that allow me to have an overall algorithmic approach that leverages that ability in a way that I can't do just classically. And even though I'm leveraging both quantum and classical, gives me a significant advantage. We talk for a couple minutes on. So another really interesting research area is, can I leverage AI in creating AI models, in order to do optimization kinds of problems? And one of the interesting things that they're looking at, similar area to the quantum algorithm, is nonlinear optimization over graphs as one example. So an example of this is why this real world problem is optimum power flow in a complex network. It's very, very challenging to solve that numerically, especially with near time operational settings that you want to do. So you want to basically find the economically optimal output set point of all the generators. So all the load and physical constraints are met, like all the stuff below that you have to meet those constraints. And the approach that people are looking at, like IBM Research and other places, is coming up with basically leveraging graph neural nets with some corrective steps in there where you're adding task specific constraints, transforming it so you can put the constraints on and transferring it back into the graph neural network and keep going. And it's showing some very interesting results. Like at IBM Research, they came up with a model with 20 million parameters based on historic and synthetic optimal power flow data. It's much more faster to give you basically the answer than the state-of-the-art classical optimizers with very similar optimality gaps. And they benchmarked it on a whole bunch of instances with several thousand nodes. So this is just give you like a little bit of a snippet of a taste, for the AI thread of this, of leveraging these trained models to basically give you a answer much faster than a more classical combinatorial optimization or graph optimization algorithm. Okay, so I'm going to wrap up and then leave a little bit of time for questions. Quantum is real and rapidly advancing. We strongly believe it's going to provide a new computational tool for data science and for optimization. Both quantum and AI are both giving an opportunity to approach problems in a new way. It's a very exciting field in both of these, but benchmarking is key to determining which optimization approach is best. So it's a really exciting time in optimization for a couple reasons. The first reason is, although we've been doing optimization for a long time, there are still a lot of places where there's a lot of value to be unlocked by doing it better. And we're now at the point where we've got AI as a readily accessible computational tool and quantum as an emerging computational tool, which allows you to take very different approaches than we've done in the past to potentially go after those areas where optimization can be better than it currently is. So thank you for the time, and I hope this was valuable.
Yeah, thanks, Scott. It was an amazing talk. Thank you so much for sharing your insights. Please post your questions for Scott on Discord channel. Everyone, I can get started with like one of my own questions. So in terms kind of in the near term, right, where do you kind of expect the main benefit to come from using quantum algorithms, especially for optimization? Like, is it going to be in terms of like reaching better local optimas or time to solution? or something else?
I think it will, and this is a little bit softer, so it's like a little trickier to prove, but I think where the quantum approaches are going to provide the most value is by very rapidly sampling and getting a large number of good potential answers that give you a basically kind of like that multi-objective optimization piece, like a better idea of a full Pareto front. So, for example, classical optimization is really good at, like, if you have one constraint, which say return on investment for a portfolio, classical approximate are really pretty good. And you need to get to like massive numbers of variables before you get far off of optimality. But what classical approaches are not quite as good for is, can you find a significantly lower risk answer that might be slightly off of the best return? And oversimplifying a little bit, but a quantum approach may do a better job for those types of kind of situations. So I think that's probably going to be more likely true in the near term for those like kind of scenarios. So and it's definitely going to be in situations where you're using quantum and classical together. Because the quantum approaches, at least for the near term, I don't think are going to give you like the fastest path to the optimal solution, but they may give you a much, much faster, when used with classical, either runtime to get to the optimal solution under multiple constraints, or like a better, very much faster getting to a Pareto front or an interesting Pareto front.
Okay, yeah, thank you. We have a few questions coming in on Discord. It's a question from Dhanalakshmi. How do we decide whether a problem should be solved using classical methods, AI, or quantum methods?
Really good question. So I think a little bit different answer for the two of them. So for the AI approaches, I think it's complex situation where you've got either a lot of synthetic data that you trust or a lot of historical data that you can rely on. And the computation using a classical approach is going to be really, really heavy, and getting close to optimality very, very fast has significant advantages. That kind of problem, like the example I gave for the energy grid, I think, the AI type approaches are really interesting from my perspective. For quantum, I think it's in the near term, those problems that blow up on you really, really fast. I think a lot of the early work in quantum, like I mentioned before, was really focused at, can I do, instead of 1,000 variables, 2,000 variables, because CPLEX breaks at 1,300 variables. I don't think those are the ones that are in the long term. Quantum, and we should still look at it in the long term, I think quantum will be good at that. But in the near term, I think it's more like those list of the 10 areas in, let me see if I go back to it. The list of the 10 areas that you got over here on the right, like the market split labs, Birkhoff, Steiner trees, et cetera, et cetera. Those are examples of problems because of the nature of the problem blow up on you on relatively small number of variables. And those are the problems I would look at first for quantum for those. Again, as anything else, if you also want to look for the problems where classical is not quite as good as you would like, but also, a relatively small percentage improvement is worth a huge amount. Just from a pure value point of view, those are all the problems that are more interesting.
Thank you. A question from Srinikesh. Does quantum help to collapse the NP space to P?
No.
Thank you. Okay, so question from Samanvit. In deep learning, we have like nonlinearity, for example, with neural networks, which help solve the problem. And in quantum, can we completely really get over the nonlinearity, and how it's solved? Like basically, I guess, how is nonlinearity handled efficiently?
Probably not deep enough of a algorithmic expert to give you a good answer for that question. Yeah, so I'm not gonna try.
Okay, that's fair. Yeah. Thank you. Question from Sunil. How can we get the quadratic speed up? Is it possible, like just by working on error correction?
Yeah, I think the challenge with the quadratic speed up is, remember, so you can think of quantum computing and classical computing having different flywheels, right? So your classical computer has a flywheel that's like sub 1 nanosecond. Your fastest quantum computers are going to be somewhere between 100 nanoseconds and 1,000 nanoseconds. So somewhere between 100 and 1,000 times slower. And that's for like the fast ones, like spin, superconducting qubits, et cetera, et cetera. The slow ones, you're talking about another 1,000 to 10,000 times slower. So the issue with the quadratic ones is that certain modalities will just forget it. Like if you're a million times slower flywheel, you're, again, biased, I admit, but you're just never going to get there on a quadratic speed up. If you're like 100 times, maybe you will, maybe you won't. Quadratic still can get to large numbers, so maybe you will, but it's going to be harder. So the error correction fault tolerance will allow you to run much deeper programs and you can think of that as giving you much more accurate results. So yes, it will allow you to run Grover's algorithm more accurately, run denser matrices in the future, but it doesn't solve the underlying, you got to make up the fact that it's slower to start. So I do believe that for the faster qubit modalities, you probably will have some advantages from Grover type algorithms in the future. But it's not just the error correction that allows you to run more accurate programs. It also depends very much on the problem set and the scale, because you need to get to much larger scale in order to make up the time.
Thank you. Another question from Yugandhar from India. Can you talk a little bit about kind of comparing the different modalities like superconducting, photonic versus ion traps?
Yeah, so I mean, I kind of hit on it a little bit there. I mean, inherently, there's in our minds, three major things. So one of them is we're building computers. In quantum, we completely lose sight of that most of the time because most people are just thinking about existence theorems. Like, do you have a quantum computer that can at one point in time run a really cool program? But what we're trying to do is build a new computational tool for the world to use. So we're trying to build computers. What's the number one metric for a computer? Throughput. So speed is the most important thing that drives cost efficiency, blah, 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 usefulness, et cetera, et cetera, et cetera. With qubits, there's a trade-off between speed and coherence, and you're always trading them off. Because I can give you something that holds a quantum state forever, but that's also something I cannot program. So it has no value whatsoever as a computer. So the modalities on the speed thing are trade-off between programmability and coherence time. We tend to think that if you can get the same effective error rate, you should pick the fastest one because that will make the best computer. The second major kind of characteristic that you want to think about is manufacturability and scaling. Can you build a very large scale modular system out of this technology? Not just can you, again, have an existence proof on one, but is your underlying qubit technology allow you to cost efficiently build a large scale system? And then there's differences there too. Like our bias is more towards the silicon manufacturing based qubits, just because we think that they're a lot more manufacturable than some of the other approaches, but differences of opinions there as well. But those are kind of like the two major trade-offs there. Photonics is very interesting. I think it's farther away from people showing large scale systems that you can beat classical. I think the ones that are closest are superconducting, which by the way is also the youngest of the technologies, trapped ions and neutral atoms. Those are the three that are the ones that are like most advanced from the point of view of having systems out there that people can run.
Okay. Thank you. I think we have time for one last question, maybe a broad one. It's kind of two questions from Chaitra and from Charan that I'm kind of combining it to one. So how long will it take for the global ecosystem and workforce to fully adapt to this new technology? And while many students are kind of excited about quantum computing, but feel overwhelmed by like the lack of like a clear roadmap, and if you're starting today as a student, what step-by-step path would you follow to build the right skills, find the right resources, gain research experience, and eventually get a quantum job?
Sure. Well, there's lots of different kinds of quantum jobs, so that's a tricky question because, like in the computer industry, you've got people building wafers, you got people building systems, you got people writing system software, you got people writing algorithms, et cetera, et cetera, et cetera. So that one, it depends. It's like the underlying domain expertise in each of those pieces, and then the quantum expertise on top. All right, so try to do this as a short answer, but like it's really interesting what's happened over the last 7 or 8 years. Like I put a lot of effort into training and upskilling, and like honestly, 8 years ago, a lot of effort into like in-person hackathons, et cetera, et cetera. COVID hit, massive shift to digital education like this. So a lot of focus on digital education, digital training, et cetera, et cetera. Then the Chat GPT happened, and basically now making people understand how to program Qiskit line by line by line is actually less important than, because you can leverage AI to do a lot of that. Like I've tried just test every once in a while, go onto my AI coding assistant of choice, type in write me a quantum program to simulate the ground state energy of lithium carbide and run it on a real quantum computer. If it's based on IBM Quantum, you can actually be up and live and running it, like and getting your account and everything within like 15 minutes and taking that program and running it. So that actually, the barrier to that is much, much lower. The more challenging thing, and I think where the training and skill development education comes from, is for the understanding the underlying math and understanding the algorithms and the algorithmic implementation, because that's where a lot of the innovation is going to be over the next little bit. It's very similar to like data scientists and optimization, experts. Like there's a lot of art still in optimization, understanding your data set, understanding what approach would be the best, understanding like how to write an objective function and constraints in the most, way, which optimization approach is the best. Those kinds of things, I think, are really critical skills and actually much more rare than the skill of, can somebody write in Qiskit, which we can teach people to do that in a couple of months. It's really building the skills and the domain expertise and building the math skills so you basically have that foundation. Like that would be my advice for like the majority of the quantum enabled like unlock is going to be really those people who understand domain and understand the math and understand how to apply the quantum algorithm to that domain. So hopefully that was a helpful answer, but especially with the rise of AI, it's still important to understand the programming. Like, please don't get me wrong, but it's really making it much more rapidly to have people advance to the point where they can very rapidly get programs written to run on a quantum computer. The trick is getting them to run well on a quantum computer. And the trick is the same trick as any of the classical optimization heuristic approaches of understanding the art around that, as well as the science.
Yeah. No, thank you so much. Yeah, I think that really resonates with me. I agree with that. Thank you. Yeah, we have a lot more questions in the chat, but like I don't think we're going to have the time to go over them. If you don't mind, we would be happy to send them over to you. And
Okay.
if you have the time, yeah, that'd
Yep.
be great. Yeah, thank you so much, Scott, like for joining us today and for like kicking off our program on such a high note. It was wonderful to have you here and to like, thank you for taking the time to share your insights with us.
Oh, it's absolutely my pleasure. Like I said, this is why I got into quantum because I'm passionate about doing this, right? So thank you and excited for all you.
Thank you.
Yeah. Thank you, Scott.